Hello guys, welcome back. Today we're going to go over Fermat's principle. So this is a quote by Pierre de Fermat that says the actual path between 2 points taken by a light ray is the one which is traversed in the least time. Well, we'll see how this changes this statement, but let's start at the basics. So in order to use Fermat's principle, we need to kind of know how the refractive index, so how fast the light is traveling in the medium. So let's just say these 2 points here, they've got a light going between them, are in air. Now it'll be different if they were in some ice or some water, for example. So in order for us to calculate the refractive index, we need to use this equation at the bottom, which is the speed of the light in the vacuum divided by the speed of the light in the medium. And we'll usually see that n is greater than or equal to 1, as 1 is kind of our basic vacuum refractive index number, and most things travel slower than they would do in a vacuum. So here's a table of some refractive indexes. As you can see, vacuum is 1, and then air is actually really close to a vacuum. But then this is only kind of, they're all quite low, but like benzene, it's 1.5, which is quite different to 1. And it does actually have an effect. You will be able to see it if you look at some things online and stuff. Also interesting note is that the refractive index of ice is less than water, and this is due to the ice having a lower optical density than the water. So things that can affect Fermat's principle, there's certain things. So if you have a moving fluid, that requires some modification. I won't go over that, but that just does. Dispersive media, so that has different philosophies for different wavelengths. You kind of have to fix the frequency of the light, and then the time of travel does not have to be minimal, but the stationary path does. So that immediately counteracts what the statement at the start says about being minimal time. So this all leads to the modern day statement of Fermat's principle, saying that the path taken by the light ray is such that the optical path length is stationary, so it's approximately equal to another adjacent path. Now, to calculate the optical path length, there's two ways of doing it. There's one where the refractive index in the medium is constant, and one where it changes. And so one where it changes, you have this integral of the refractive index with dl, which is your line element. So we imagine breaking your segments into small pieces, and then your refractive index changes as you go along that. So that gives you your optical path length. Or if n is constant, then you just times it by the length between the 2 points. Now, we can determine the time travel and the path of the light in a medium with constant refractive index. I won't go into anything with a medium with a changing refractive index, because it's a bit too advanced. But here you can see that we have 2 points, and for us to calculate the time travel, we do the geometric length divided by speed, which is just distance divided by speed equals time, as we know by that. And our speed, we can use our equation from before and rearrange it to get n over c. Well, it'll be divided by c over n, but to times it you just flip. So you can see that our n and our c's are constant, so we got our refractive index is constant and our speed of light is constant, obviously. And so we just need to find, to get the smallest time taken, we need to find a path with a minimal geometric length. Excuse me. And we know that between 2 points, the shortest length is always a straight line. And therefore, this means that mediums with a constant refractive index always produce straight lines for their fastest time travel. Thank you for watching. Make sure you hit like and subscribe, comment anything you'd like to see, and I'll see you guys in the next video. Goodbye.